There are moments in science when the universe seems to whisper, "You've misunderstood everything," and then it shows you why. One such moment happened when physicists stumbled upon a particle that defied expectations, not because it was powerful or dangerous, but because it simply shouldn't exist. Not under the rules we thought governed everything. We build our understanding of the world on equations, neat, precise, and often beautiful. But sometimes something emerges from the chaos that doesn't fit. Something that cracks the framework, exposes the hidden seams in reality, or rather, in what we thought reality was. This is the story of that particle. A particle so strange, its existence questioned the very foundation of what we know about matter, energy, and even causality itself. To understand why it shook the scientific world, we need to go back, not to the Big Bang, but to something just as mysterious, the vacuum. Because in quantum physics, a vacuum isn't empty. It's alive. It seethes with energy, invisible, untouchable, but always present. A wild ocean of probabilities where particles blink in and out of existence, without warning, without cause. According to quantum field theory, even the most empty part of space is anything but. Virtual particles are constantly being born and annihilated. They appear from nowhere, last for a blink of time, and disappear again as if nothing happened. They don't follow the normal rules of matter. They don't obey conservation laws the way normal particles do, and yet their effects are real. We can measure their influence. We can see what they leave behind. It was in this strange, chaotic background that a theoretical particle was proposed. Not seen, not captured, not even confirmed. But the math said it could be there, and the math was terrified. Because this particle wasn't just improbable. It broke the rules. Its mass was imaginary. Its behavior violated causality. And if it existed, really existed, it could travel faster than light. This wasn't just a crack in the standard model. It was a threat to the very structure of time and space. Its name? Tachyon. Tachyons were first introduced as a mathematical curiosity, a possible solution within the framework of special relativity. But they came with a price. In theory, they could never slow down to the speed of light, only exceed it. And that alone turned physics upside down. Because if something could go faster than light, it could also go backward in time. And if information could travel into the past, then cause and effect would break. Events could happen before their triggers. Reality could become a loop, an inconsistency, a paradox without resolution. Einstein's relativity doesn't forbid the existence of faster-than-light objects. It simply makes them dangerous to logic itself. So scientists did what they often do with uncomfortable possibilities. They buried them in footnotes, filed them under interesting but impossible, a glitch in the math, a hypothetical with no place in the real world. But the universe wasn't done. Decades later, while studying high-energy collisions and quantum fields, the idea of particles appearing from nowhere gained traction again. Some results, subtle anomalies in particle behavior, hinted at brief violations of expected energy conditions. Particles seemed to appear before they were supposed to. Waves shifted phase in ways that suggested motion faster than c. The math didn't scream tachyon, but it whispered it. And then came string theory, an attempt to unify all forces of nature into a single framework, elegant and consistent. But in its early versions, something strange emerged. The lowest energy state of certain strings wasn't a normal particle. It was a tachyon. In string theory, tachyons weren't just allowed, they were inevitable. And that terrified physicists all over again. Because it meant that the theory, the whole theory, was unstable. If tachyons existed within the equations, then the universe they described wasn't in balance. It was like building a skyscraper on a sinkhole. But here's the twist. Some theorists began to see tachyons differently, not as destructive forces, but as signals, warnings from the math. Clues that the system needed to evolve to transition to a more stable state. In this view, tachyons weren't mistakes. They were messengers, the signposts of transformation. Just like radioactive atoms decay into something more stable, a tachyon-filled vacuum could collapse into something new, a new state of reality, a new configuration of space and time. This idea that tachyons might not be the end of a theory, but the beginning of a transformation, changed everything. It gave birth to the concept of tachyon condensation. Think of it like this. Imagine you're walking on a frozen lake. The surface seems solid, stable, but suddenly cracks begin to form beneath your feet. They spread fast and unpredictable. It's terrifying, but those cracks aren't just signs of collapse. They're signals that something beneath the surface is ready to break free, something waiting to become more stable than what was holding you up. In physics, tachyon condensation is the process by which an unstable field, full of hypothetical tachyons, reorganizes itself into something new, a different ground state, a more stable vacuum. The universe recalibrated. And this idea wasn't just poetic. It had consequences. In certain versions of string theory, entire dimensions could vanish or emerge depending on how the tachyons behaved. The presence of these impossible particles could signal the death of one version of space-time and the birth of another. It was as if the universe had a hidden flexibility, a willingness to rebuild itself when it became too unstable to go on. Suddenly, tachyons weren't monsters breaking the rules. They were midwives of change. They represented instability, yes, but also evolution, the process by which the universe might shift into new forms. But even as theorists began embracing this interpretation, a question lingered in the background. What if tachyons weren't just abstract tools of mathematics? What if they were real? This is where the story becomes dangerous. Because if tachyons exist as physical particles, not just as instability signals in theoretical fields, then everything changes. Let's imagine for a moment that a tachyon could be created or detected in a lab. Not in a simulation, not in an equation, but in reality. What would happen? First, its motion would break every classical intuition we have. It would always move faster than light. We couldn't catch it. We couldn't stop it. It wouldn't obey any normal causality. To an outside observer, it might look like the particle appears at its destination before it even begins its journey. In fact, it might not have a start or end point at all, only a blur of presence smeared across space-time like a signature written before the hand touches the pen. Second, communication with a tachyon could, in theory, allow for messages sent into the past. This would break one of the deepest assumptions of physics, that cause precedes effect. Imagine sending a signal today and receiving the reply yesterday. Imagine changing an outcome before it happens. Imagine the paradoxes. Physicists call this the causal paradox, and it's one of the biggest reasons why the scientific community is wary of anything that even hints at faster-than-light interaction. Not because it's mathematically impossible, but because it destroys coherence. And yet, the equations still allow it. Relativity doesn't forbid tachyons. Quantum theory doesn't forbid them either. The problem isn't the math, it's the implications. The universe, as we know it, is built on causality, the idea that actions lead to consequences, not the other way around. If you break that chain, you don't just bend physics, you shatter it. But here's the most fascinating part. Some physicists believe that the universe already protects itself, that even if tachyons exist, nature has built-in mechanisms to prevent causality violations from manifesting in observable ways. They call this the chronology protection conjecture, the idea that reality will always find a way to preserve consistency, to patch over the cracks before paradoxes can unravel the fabric of space-time. So maybe tachyons do exist, maybe they dance at the edges of possibility, always out of reach. Maybe they shape the evolution of quantum fields and then vanish before they can cause chaos. Or maybe they're not particles at all. Some researchers now think that tachyons are not things in the traditional sense. They're signals, indicators, mathematical flags that say, this version of the universe is unstable. Get ready for a shift, like turbulence before a storm. or a tremor before an earthquake. They don't carry energy or information. They carry warnings. And if we understand them, we might understand something deeper about the universe. That instability is not failure, it's transition. A sign that something better, stronger, more coherent is coming, but only if the system is allowed to evolve. This is where physics meets philosophy. Because in many ways, tachyons reflect a truth we experience as humans too. We fear instability. We fear what doesn't fit. We resist the cracks, the signs that something is changing. But maybe those cracks aren't signs of collapse. Maybe they're the start of something new. In the quantum world, nothing is ever truly at rest. Everything is always in flux, uncertain, shifting, reborn in every moment. And sometimes, it's the particle that wasn't meant to be that shows us what the universe is really capable of. If tachyons are messengers of instability, then perhaps instability is not an error of the universe, but its mechanism for evolution. Think about this. Everything we know to be stable today was once unstable. Atoms didn't always exist. The universe didn't always have structure. The laws of physics themselves may have emerged from chaotic, fluctuating states. States that only settled into coherence after a phase of intense imbalance. What if tachyons are echoes of that process, remnants of a deeper physics we haven't yet uncovered? In some theoretical models, the early universe, just fractions of a second after the Big Bang, was filled with unstable fields. The cosmos was a storm of raw energy, undefined forces, and strange symmetries on the verge of collapse. And it was during this time, theorists believe, that tachyon-like instabilities may have played a critical role. They could have driven the transitions that gave rise to the particles, forces, and constants we observe today. In other words, tachyons may have helped sculpt the rules of existence, not as particles we could ever isolate in a lab, but as mechanisms, temporary, untouchable, yet essential. The vacuum itself may have once been different. Our universe may not be in the only possible vacuum, only the most stable one we know of. And if that's true, then it could shift again. That idea terrifies some physicists. Because if our vacuum isn't the ultimate ground state, if there's a deeper, more stable vacuum below it, then we live in what's called a false vacuum. And a false vacuum, by definition, can decay. Maybe not today. Maybe not for billions of years. But in a universe where instability can exist, so can phase transitions, massive, instantaneous shifts in the nature of space itself. Theoretical physicists have even proposed the idea of vacuum decay bubbles, expanding spheres that could emerge anywhere in the universe, annihilating everything in their path as reality itself rewrites its fundamental rules, all because a lower energy state becomes available. All because the universe decides to evolve again. And what would trigger such a shift? In some models, it's tachyonic instability, the signal that the false vacuum has reached its limit, and that a more stable configuration must emerge. Again, tachyons appear not as agents of destruction, but as harbingers of renewal. They don't destroy reality. They expose its impermanence, a reminder that even the most solid foundations we trust, time, space, energy, may one day transform into something else entirely. Not by accident, but by design. Because the laws of physics are not sacred. They're not immune to change. They're emergent properties, shaped by fields, forces, and interactions that themselves can evolve. And every now and then, something in the math tells us, you're standing on shifting ground. That something might be a tachyon. We like to believe the universe is fixed, that its rules are permanent, that what we discover is the final truth, not just a stepping stone. But every great leap in science has shown us otherwise. We once believed time was absolute. We once believed atoms were indivisible. We once believed space was empty. And now we know none of that is true. What if tachyons are just another step in that unraveling? Another glimpse beyond the curtain of what we think is possible? They challenge not just our theories, but our instincts. They suggest that the universe may not be a closed system of laws, but a living, shifting landscape of probabilities, fields, and transitions. They remind us that even our most trusted equations can be incomplete. That nature doesn't care if something makes sense. It only cares if it is. And that's the real power of the tachyon. Not that it moves faster than light, not that it breaks causality, but that it dares to exist outside the boundaries we set. That it forces us to rethink not just what's real, but what's allowable, and maybe what's necessary. Because sometimes in science, a thing is considered impossible until the moment it's not. Until a faint anomaly becomes a pattern. Until an unstable equation reveals a deeper order. Until a ghost in the math turns out to be the first sign of a new kind of truth. That's how progress works. It doesn't come from reinforcing what we already know. It comes from confronting what we don't. And tachyons, whether they're real or not, are a perfect example. They exist on the edge of our understanding, teasing us, challenging us, daring us to expand our vision. And maybe that's their true role. Not to answer a question, but to keep the question alive. To remind us that certainty is a comfort, not a truth. That the unknown isn't a void, it's a frontier. A place where the rules change, where impossible things begin. Where particles that were never meant to exist just might. So maybe the most important discoveries aren't the ones that confirm what we know, but the ones that shake us. The ones that don't belong. The ones that weren't meant to be. Because when something impossible appears, we're forced to ask the only question that ever truly matters. What else are we missing? And that question is where every great journey begins.